All right. First collaborators meeting. Not everyone could make it. That's all right. We're going to go through this. Yeah, so figured the right thing to do with this is just to kind of give an overview of all the things we've done in the last quarter. At the next meeting, these would just be monthly, so this one's a little bit lengthy. So we'll just go through a variety of things on the project updates for self. So we got 3 new models that have been implemented, tested. They have examples. They're part of the unit testing now. There's Berger's equation in 1D. That was our first one to get done. We now have linear shallow water in 2D, thanks to Garrett for knocking that out. And then we have linear Euler in 2D. The Euler in 2D as well as the shallow water in 2D are both fully GPU resident. And the way that had to be done was basically all the boundary condition methods, everything needed to have its own HIP kernel, and we needed to override some of the type bound procedures to make that happen. That significantly improves performance. It's a little bit extra work. It's not something that, like, if someone is just starting programming applications with self should be expected to do, but what we have out of the box will get the right answer. It gives reasonable performance, but some of the changes that were done to make this happen are absolutely necessary to get like really good performance. So anyways, that's what's going on there. We do have linear Euler 3D in progress. I'm just working out the no normal flow boundary conditions for that for 3D, and then we'll put in a test for that. So right now we got just a simple sound wave eruption, spherical sound wave eruption that just goes through radiation boundary conditions. That's looking good. We'll get the no normal flow stuff in there, and then that'll wrap that up. Oh yeah, getting him fully GPU resident, but that's pretty straightforward now that we understand the process to do that. Some new features in the last 3 months. These are just big ones. I mean, I'm sure there was others, but these are the ones that stood out to me. We now have structured mesh generation. So although self uses an unstructured grid representation, we can generate structured grid. So you just tell me how many grid cells you need in X, Y, and Z directions if you're in 3D. And what how big you want those elements to be, what you want your polynomial degree to be within those elements, and then it just takes care of creating that and then storing it in our unstructured grid format. You can use what's called a tiled or block layout, so you can make sub tiles or sub blocks if you're in 3D, and then those get placed in a structured manner, and that can help with domain decompositions and things like that are perhaps more efficient than if you were just to kind of stripe everything all the way to the end in X, then Y, then Z. So that's a pretty nice nifty tool for doing some first round of testing with self if you're building a new model. Very easy to use. And we now also have support creating shared object libraries rather than the static libraries. Basically once we get to V0.0.1, we'll have the a build option where you can build either a static or a shared object library. But that's actually been using the shared object library has been helpful for our development particularly. I haven't heard any complaints about that change. But basically what it allows us to do is just recompile self backend when we're trying to debug like external programs that depend on self. And then just since it's a shared object library, it'll pull in what we need to without having to rebuild our end programs. A few patches. This one was actually interesting. We met a fella at Supercomputing, very, very nice guy. He was kicking the tires with self on RISC-V architecture, and during his journey into building self for the first time, he provided some very, very useful suggestions and feedback on the code. The big one is just getting rid of this enable. We had like when you create a mesh in Self, like if you wanted to do domain decomposition, you'd have to pass in this Boolean, which in hindsight is kind of silly that it was there. This enable domain decomposition is no longer required. Basically, what we do now is if you launch even though like Self depends on MPI, you have to build Self with a flavor of MPI. You don't have to launch a Self program with MPI. You can just / my program, or you can do MPI run with one rank if that's what you want to do. But basically, we detect if you're launching the code with one process or not. And if you're launching with more than one process, the domain decomposition is automatically enabled now. So this silly flag is no longer even an optional parameter for mesh construction. So that's nice. We did get some requests to perhaps look at making some of the software dependencies optional. I know it's not on the list here, but we do have a couple issues open on our issue tracker to make HDF5 optional and to make MPI optional as well. Doing both of those will require some serious, like a little bit of effort. And what I mean by that is like for example, let's start with HDF5. If we do HDF5 restructuring, so where like if someone didn't want to install HDF5, we would need to provide some kind of file IO format for that. And then that means also in PySelf, we would need to have a reader that can handle that file IO format. So that doubles the work on the post-processing. So I'm not as inclined to make that happen, but it's, if there was enough votes in that direction, we would certainly do it. But yeah, there's a few bits, there's a few wrinkles on that one. MPI is probably less challenging to do. However, like we would just basically need to provide some like MPI stubs for the MPI API components that we're using, which is basically the init, comrank, comsize. I think we have MPI wait all and ISend and IReceive. So like one route to go would just be to provide stubs that basically do nothing, but they expose those subroutines to Self in the event MPI is not being used. The other route would be to kind of do what we did for the various backends and just split out subdirectories and conditionally compile the application, the library based off of whether or not someone wants MPI or even has MPI on their system. So like I'm definitely thinking about doing that. Anything to help lower the barrier to entry to like installing and running Self. I understand like software dependencies can cause some headaches, and so we do take that very seriously. Like we don't want this to be a problem to get the code up and running. But it will take some effort. It's probably not something we'll do this year, but who knows? Maybe I get 2 weeks of rest for the holiday break, and I'll come back and be ready to do it. So that's kind of those kinds of things to get myself back on track here. There was some missing do concurrence in the Self DG model module. So higher up in Self, we still had retained our tightly nested loops, and so we did find that in some testing. And just went back through and just replaced those with do concurrent. So those are all now multi-threaded. So that's good. On the workflows, so these are all things, when I say workflows, these are all things that like GitHub Actions or our stuff on Google Cloud Build, what those do. Some of the new things that we added in the last 3 months are automatic publication of the docs. So this is both the make docs that you see at self.fluidnumerics.com, as well as the Ford documentation that you can link to from there. So we added a GitHub workflow to generate the Ford documentation on the fly and then do a make docs publish from there. So that's nice. So we don't have to do that manually anymore. There's now a pre-commit hook. It's not a requirement that everyone enables this. In the contributing.md now, there's a couple changes there to the contributing docs that show how to set that up if you want it. But what this allows you to do is prior to, or at the moment you're doing a git commit, this will run a script underneath to apply the formatting for with fprettify that fits our standards. So it helps you pass those fprettify build checks when you submit a PR to self. So it's just a helpful tool if you want to use it. Otherwise, you can continue just using fprettify on the source, test, and examples directory, and you'll be fine. We've currently disabled CI for NVIDIA and Intel compilers. We were finding segmentation faults, particularly with how we were doing. Like it seemed to occur in areas where we start to have like multiple child classes coming off to basically get to a model instantiation. And the NVHPC compiler actually seg faults. We do have an open issue on self's issue tracker for this. I have brought it up to NVIDIA, and the request was that we just try it with the latest NVHPC again and see if it's still an issue. Since this was about 4 months ago, and I only recently brought it up to them. So we'll give that a try with the newer compiler, and if it still happens, we'll open up a bug report with them and see if we can get that resolved. So yeah, so it's always fun when you brick a compiler. All right. That's what we've done. Now we're going to pivot to trying to predict the future. So the past is a particle, the future is a wave. We'll see what actually collapses on that probability distribution here. Looking ahead, this is our plan. First version release will be out before Christmas. So Merry Christmas, everyone. Tagged release of self. There's only a few things left on that list where I think we'll be happy just going ahead and tagging that release. Like I mentioned up top, we're going to finalize up that linear Euler 3D. There's some compiler warnings about unused variables and some of the lower end modules in self that are, it needs some cleanup. And then we've got some API docs to wrap up there, at least down on the self, what I would call the core of self. So that should improve the forward documentation. That will get us to a tagged release. There will initially not be any packaged builds in that, but what we plan to do in early next year is to work towards getting a variety of packaged builds for you just to click and download and be off and running with. This will include tarballs, Debian, .deb files, .rpm, so you can be, use your apt or Yum package manager to install self. We're also going to have some Docker images for a variety of platforms. Those Docker images will cover NVIDIA GPUs and AMD GPUs, as well as CPU-only platforms. And then for those of you who are collaborators with us, we'll open up our Docker image registry to you on Google Cloud, as well as the GCP VM images and the Terraform infrastructure as code, so you can easily deploy self on either single instance deployments on Google Cloud, or you can use auto scaling Slurm GCP to run self. We are planning on putting together some benchmark numbers for that on a variety of GPUs that are available on GCP, including the V100s, A100s, and H100 GPUs for a few of our pre-canned examples, just so you have an idea of not just runtime, but as well as cost per simulation as a function of grid size, model that you're choosing, and the polynomial degree, etc. So we're working on putting that together. It's a tall order to fill, but like I said, probability distribution, we're going to see what things collapse on this wave. Other upcoming things, aside from our packaged builds and things like that, we've got a couple new models that we're planning, nonlinear Euler 2D and 3D, nonlinear shallow water 2D. I should have added it to the list. Actually, I'll probably do that now. We're working on some sediment transport stuff. Just been doing a lot of reading these days, wrap my head around how this is going to be done. So one of our collaborators at Virginia Tech had requested this. So we're spinning our wheels, just trying to wrap our heads around this problem and see how we could implement it as a conservation law. Shouldn't be too challenging, because my understanding is it looks basically like we can use compressible oiler or an incompressible solver, and then tracking the interface looks like an advection diffusion problem. So that should be pretty straightforward. Should's a dirty word, I guess. Black Scholes, for those of you who are into like options tradings and things like that. I remember learning about this years ago, and it always felt like a really smart way to gamble. Might as well make some tools that run on GPUs that help you gamble even smarter. So yeah, we're gonna look into doing that. I think the classic example that everyone starts with is the European put option. I'm still learning all this stuff, but yeah, we're gonna take a crack at that, see what we can do in the financial realm. We have an open issue on the GitHub repository. I've identified a few, like our MPI implementation is fairly basic. I mean, it uses asynchronous point-to-point messaging, so I send, I receive pairs with await all. But the way we use that right now is it's basically as good as if you did send and receive blocking, in the sense that the wait all is called right after all the I send, I receive pairs. There are opportunities to move that around, to move that wait all further away from the I send, I receive pairs, and hide some of the communication costs behind computation. So that's one realm. There's two other things we're looking at, is looking at using MPI data types to help package up the messages more efficiently, to more fully utilize the bandwidth, particularly in 2D. We have very, very tiny messages. Basically, each message is an array that's of length polynomial degree plus 1. So, in the case of like n equals 7, this would be a message of length 8. If you're using doubles, that's only 64 bytes. They're very, very small, so they're just not going to ever really fully utilize the bandwidth of any networking hardware, any modern networking hardware. So getting us over to the MPI data types would likely help with that. And I'm already blanking on the third optimization. But anyways, if you check out the self GitHub repository, we have that issue up there, discussing all the various things that we're looking at. If you have suggestions or comments on that, definitely just go to that GitHub issue. Let me see if I can find it, actually. Pull it up on the screen here. Definitely looking for feedback on that if anyone else has got experience in this realm. It's always good to bounce your ideas off of folks. All right, let me share this tab. This is issue number 84. Oh, right, yeah. The last one was actually on the process placement. So because our mesh doesn't move over time, yet we're not doing AMR yet. It is on my list, but that might be a long-term goal. So for now, since our mesh doesn't move, we know a priori what the communication patterns are, so we know which rank communicates to. We know which ranks communicate to each other, and we can use that to create a communication graph. An MPI can use that information as well as the topology of your hardware to determine your process placement that puts things that communicate a lot as close together as possible. So those are the three avenues that we're interested in exploring here to improve MPI performance, which will ultimately help scalability. To get there, we're going to start putting together some benchmarks that do scaling tests, so we have a baseline to measure from. And as we do each one of these individual things, we'll kind of see what the impact is and determine whether or not to keep it. So that's what's going on there. We've also got, 2-point vectors. This has been on my list for a long time. I had them in at one point, but wasn't quite happy with the implementation. And since we're just kind of like, we've been in this experimental mindset for a bit, I was just quite happy just to like remove it and say, look, let's just do it right later. Well, that later is becoming now very soon. So we're going to put 2-point vectors in there, and then the associated methods with that are going to be primarily the divergence operators, so that we can do 2-point vector flux divergence, which allows us to then implement entropy conserving schemes, which is going to be very exciting to see how this all compares to our conservative formulations in the nonlinear Euler model. Definitely a very, very big learning experience for us. So that's the gist of what's going on. We do have a few other things I'll just plug real quick. I'll post the link probably in the description of the video on YouTube. We do have a little fundraiser going on. In case you don't want to just be a backer or whatever, if you want a cool shirt, you can support the Spectral Element Library in Fortran by getting the shirt that says "Friends Don't Let Friends Write in C++." And that's an odd thing for me to say because like half of our code, I could argue, is in C++ technically because we're writing HIP kernels, but still. Maybe AMD will get the message. We've only got one sold so far. We've got 11 days to go, so pick up that shirt before Christmas and help support our project and get a cool shirt along the way. I guess what we could do now, since it's just you and me, Garrett, is there anything you want to talk about self-related?
Self-related things. I will mention the model type that I've sort of been talking up for a few weeks and have yet to act on, but that would be axisymmetric Euler equations. And a lot of the holdup for that is being very clear about the derivation. As you know, like if you go to the self-documentation in tutorials, I think that those examples provide a lot of background, like mathematical background and formulation in terms of actually like getting to the implementation of the model. And I want to be very clear about how we arrive at axisymmetric flow for Euler equations. Another minor hang up, not really hanging up, but just thinking about it. Item on the to-do list is implementing a middle axis boundary condition, because that behaves differently than what we have currently implemented. So that's the biggest thing in terms of like model implementation. Aside from that, I know that we've been sort of lightly been discussing like different ways to benchmark things. And I've mentioned before that there's a set of Riemann problems for the Euler equations in, I can't remember the full name of the book, but the author is Toro, which is a fairly well-regarded CFD textbook that has a very popular chapter on like on Riemann problems for Euler equations and implementing flux vector splitting and row solvers and other things. But they provide a set of test cases as well as like, you know, they discuss the Sot shock problem. So I'm just throwing the hat out there again as potential benchmarks for when we get nonlinear Euler going. It seems to be fairly standard. I know that there's another fluids code called Cholla, Cholla, that sort of discusses this exact chapter in the paper form, the published paper form of their software. But besides that, I don't think there's anything else major that sticks out to me.
Yeah, as you were mentioning this, I was like, wow, hang on a second. We just did a live stream on this. We have some mesh generation tools now that
course,
Garrett wrote. I'll let you speak to that in a minute. The other bits of it is I think right now, so our workflow for getting meshes into self is like you can either do structured mesh generation with our inbuilt stuff, or you can pass anything that's compatible with Hopper, the high order preprocessor. You can pass those meshes into Hopper, and then we can read Hopper meshes. That's fine. One of the mesh generators we use quite often is Hoke Mesh from the Trixie project. And so I think we're going to be putting in just a direct Hoke Mesh reader for 2D and 3D, just to provide that as an option again. But yeah, Garrett, if you want to take a minute and talk about the little tool the tool you put together for Hoke Mesh.
Yeah, so it's really not, as you said, it is a little tool, but quite useful. Basically, the underlying workflow is that in Inkscape, which is a vector graphics editor, you can sort of create an SVG with certain constraints, like using layers, labeling layers as like inner boundary, outer boundary, and these types of things, and checking a few other things. But essentially, you can go straight from SVG. You can parse SVGs into 2D meshes using Hoke Mesh, which is it's just a nice workflow. I think of like being able to like the simple example. Well, like the icon right is a pumpkin, so you can get sort of these like incredibly novel 2D meshes, 2D domains quite quickly. And I found the workflow to be quite nice. Like even for like simple things like quickly, it sort of provides a quick and dirty way to check out like the effects of like simple geometry. So like if you have like a square domain or like a circle domain, and then you have like a triangle and a circle in that, and you sort of like just like slowly like edge them towards edge them towards each other, you can sort of like feel out in a non-programmatic way the effects of that once you pass it. So it's like you draw it and you pass it through Hoke Mesh and pass it through Hopper.
Yeah, no, it's kind of neat because like you can just, I don't know, I've always had this dream of just like sitting at like even just a notepad and just drawing it, snapping a picture, and then like, all right, let's make a mesh and solve a PDE on it. That'd be sick.
Yeah.
And this like to me is like a step closer to that. Is at the very least, it's like, okay, grab a Wacom tablet, or hell, if you're fine, you don't have a Wacom tablet, use your mouse pad. Draw up something in a artistic piece of software that's designed for drawing things. Get it out of your mind.
Yeah.
And rough out your idea. Do some simulations on it, and then use that as your refinement process. It's kind of cool. I mean, it definitely is similar to like the CAD workflow of like, all right, build your geometry, then mesh it, then run it. But this is a way to do it without like expensive software. So it's really, really cool.
Yeah. And it's only like 300 lines of Python, which is kind of incredible.
Yeah, no, that's great. Now I'm waiting for the day where I can talk to a Furby on my desk and say, "Hey, Furby, this is kind of what I'm thinking. Can you draw me up a file in Inkscape, and then you can edit it and let your AI Furby, do this for you, and then you can generate your mesh. And who knows? Maybe Furbies will be running simulations in the future. Who knows? I have a weird mind, I guess. All right. Yeah, so this is Hoke Mesh. For those of you who are interested, it's at the Trixie framework, Hoke Mesh. And that repository Garrett's been talking about is SVG to Hoke Mesh. It's on Fluid Numeric's GitHub. So yeah, check those out. But I think it's just about everything that's going on that we think will be going on. We will have our next monthly meeting soon. Those of you who are collaborators will send out a calendar invite for that. We have a few time zones in our group, which I think is part of the problem. That, and right now it's December. It's like everyone I think is on the wind down. So that's all good. But we'll try to accommodate time zones next time, and hopefully we'll have some more exciting things to talk about. Definitely looking for any feedback on the code, models people want to see implemented, tools you want to see to make this easier to use, suggestions on build workflow, running workflow, etc. We're here to help. We want to see you guys do amazing science. So thanks for watching. Thanks for supporting our project. Talk to y'all soon.